Hi friends, my name is Vishnu Sajeevan Nair. I am here to present before you a case study to improve the dragline system by the elimination of stress formation or crack initiation in the dragline clusters, and also to reduce the formation of residual stress and propose a new design for the above said item. Now the dragline system. Considering a dragline system, there are basically four main components: the dragline boom, the bucket subsystem, the hoist ropes and the suspension ropes. Of this, the dragline boom span over a length of like 100 meters, and the bucket subsystem is attached to the dragline booms with the help of suspension ropes. And the function of hoist rope is to provide swing action to transfer the excavated material from one part to other. Now the formation of dragline boom. A standard dragline boom is basically formed by the combination of A11 clusters, that is, like there are three main chords onto which the side bracings are like directly welded, and this forms the combination of the structures form the dragline boom. Now the bucket subsystem. From the figure itself, the figure actually shows the bucket attachment of a mining system, and this highlighted part is known as bucket teeth, and these teeth are subjected to high abrasive wear, as these are the parts that come in contact with the abrasive particles being excavated, and necessary design changes has to be made on the bucket teeth so that it can withstand the formation of abrasive wear. And for this purpose, we make use of overlaying technique. That is, these bucket teeth are overlaid by different hard face alloys, so it can easily withstand the formation of abrasive wear. And it can, by designing this, we can prevent the formation of premature failure of bucket teeth, since the replacement of bucket teeth are real costly affair in a mining equipment. Now, before coming up with a new design, it's essential for us to locate the exact position of crack initiation. For this purpose, like I said before, in a dragline boom there are three main chords, and all these three main chords are air pressurized. So when a crack initiation takes place or a crack tends to move, the air tends to leak, and this eventually triggers an alarm. So the exact location of crack can be easily done, and the necessary repair activities can be carried out so that catastrophic failure or premature failure of the dragline boom can be easily avoided. Now the research question. The research question that I came up with was to how to improve the dragline system by the elimination of crack propagation, and also to propose a new design to reduce the formation of residual stresses. And for this, there are certain factors that are needed to take into consideration, like the crack propagation at the weld toes, formation of high stress concentration factors, application of finite element analysis, different weld profiles, and also different geometric parameters associated with the dragline boom. Now, coming up with a new design. As I said before, there are certain geometric parameters that are to be taken into consideration, like the thickness of main core, the fillet radius of the weld material, and so on. From the figure itself, it's quite clear. As a part of new design, we introduce a new sleeve. Like a sleeve is kind of placed inside above the dragline main core. As you can see, this is the sleeve, and onto this sleeve, the side bracings are welded, and not like the regular standard boom where the side bracings are directly being welded to the main core. So the introduction of sleeve imparts the much required mobility to the system, and also reduces the rigidity of the entire structure. Thereby the formation of residual stress is kind of like not eliminated, but it can be minimized, and premature failure of all the components can be avoided. Now continuing with the proposed design. As I said before, weld profile is a important parameter that needed to be taken into consideration. So basically, in the formation of side bracings, we make use of T-weld joint, and any irregularities in welding can result in formation of high residual stresses. And for this, and in order to eliminate this, we make use of precision welding techniques. And once performed, we can obtain a regular weld profile, and inclusion of any foreign materials in the weld material can be easily avoided. So, like in the sense, if there are any inclusion of foreign material, it can easily weaken the structure and can result in premature failure of the dragline boom. Now the experimental design. First of all, the virtual simulation of A11 cluster, which forms at the dragline boom, is done using the finite element analysis. And the next step is to locate the point of maximum stress concentration, and these points are known as crown location. And for this purpose, we make use of finite element analysis. And once these points are located, strain gauges, mechanical strain gauges are actually installed at this location so that stress distributions around the weld toes are obtained. And the geometric parameters are varied to obtain the optimum design feature. And by changing the main core diameter and keeping all other parameters constant, a significant reduction in the residual stress was obtained. And this was made part of the actual design. So the new design consisted of a new sleeve, increased diameter of the main core thickness. And this was a major feature of the new design proposed. Now the advantages that the new design poses, like because of the elimination of residual stresses, the premature failure of structure can be avoided. And as we make use of precision welding, the weld profiles are more even. There are no foreign materials being included in the weld materials to weaken the structure. And also the introduction of sleeve imparted the much required mobility to the system, which is a major factor for the reduction of formation of residual stresses. And also a combination of all this resulted in the elimination of crack formations. Now speaking about the limitations of the system. As the main core thickness increased, it actually added a significant amount of bulk to the system. So the total inertia of the system went up, and the input energy required to overcome this inertia of mass was quite high. And also the FPA analysis carried out required precise data inputs. Like if any of the inputs varied even by a smaller quantity, it does affect the design of the dragline boom and can easily weaken the structure as proposed by the new design. And also, as precision welding are carried out, it generates a significant amount of feed, and in a complex structure such as a dragline boom, it's quite difficult to conduct heat treatment process or post-weld treatment process in a cost-effective manner. And finally, the introduction of new sleeve can easily result in the increase the fatigue life, or it can prevent the premature failure of dragline components once installation is done successfully with the right precise data being inputted into the finite element analysis. So that's it. Thank you.